to 1.5%. KPR Institute of Engineering and Technology, Department of Mechanical Engineering organizes a 6-day national webinar CDS on a vision towards materials and manufacturing. In the seminar topic, today webinar on advanced composite materials for automobile and armor applications, scope and challenges. Today, our eminent resource person, Dr. V. Krishnaraj, Professor, Department of Production Engineering, PhD College of Technology, Coimbatore. He completed his mechanical engineering in Coimbatore Institute of Technology in the year of 1994. Then he completed ME Production Engineering at PhD College of Technology in the year of 1999. After that, he completed his PhD Drilling of Composite Materials, Anna University in the year of 2007. He received a postdoctoral fellowship from University of Bâle-Sabatier, France in the year of 2008 to 2009. He has published 136 reputed journals in the field of composites with the credit of 1,500 above citations with H index 16 and I-10 index 24. He has successfully carried out several sponsored research work for research establishment like DST, ISRO, ARDB, UGC, and AICT, etc. He also has a visiting researcher in the University of Bâle-Sabatier, France, and a research fellow in University of New South Wales, Australia. So once again, thank you for all the people. Sir, the forum is for yours. Thank you, sir.
Thank you, Prabhu.
Thank you, sir.
I welcome every one of you for this webinar on advanced composite materials for automobile and armor applications. Scope and challenges. Just to give an introduction about composite, it is combining polymers and reinforcements in a proper way, produces components for our use. We have many composites. If you look at composites are classified into polymer matrix composites, metal matrix composites, and ceramic matrix composites. Under polymer matrix composites, we have a lot of applications. The application ranges from aircraft components to wind turbine blades, of course, fiber glass boards, and even automobiles. Processing of composites are another important aspect to know. One popular process for making composites is vacuum assisted infusion process, where the fibers are placed on the mold and resin is made to impregnate, right? And once it impregnates the fiber, we can go for either natural curing or autoclave curing. Most of the components that are required for aerospace applications are actually produced by autoclave curing. This is an autoclave where the component, once it is infused, is placed and cured under controlled atmosphere at high temperature and pressure. Of course, it is expensive. You have other processes like filament winding, mainly for rotational parts. You can make tanks, you can make cylinders, right, where the fiber is made to pass through the resin and you can wind it on a mandrel. So I just show you a glimpse of a video how the cylindrical parts are produced. This is one of the popular process for making cylindrical parts, and you have another process which is generally called as spray molding, right, where the fiber and resin are impregnated at one particular are impregnated by spraying it on the mold. This is another process that is popularly used for making automotive components. The sprayer process gives you an idea uh, how difficult it is, or how okay. You can understand how labor intensive it is to produce components by sprayer process. Uh, if you look at the background and motivation of using composite materials for automobiles, uh, one is auto emission. The norms are becoming stringent. Then second requirement is fuel economy. Always it is good if you have a better fuel economy in your car. A lot of solutions are listed here. One is alternate fuel vehicles, but alternate fuel vehicles are expensive. Improved emission control, yes, and reduction in vehicle use. That is what we are practicing now. We don't travel. Of course, it may not be possible always. And the last option is going for vehicle weight reduction. If you look at a new generation vehicle, you can see on the left increasing customer requirements. It is mainly on safety, of course, performance. Then the third is luxury. So when you look for safety and performance, you need enhanced rigidity. Of course, everybody requires a powerful engine for performance. So this obviously leads to heavier structure. When you have heavier structure, then fuel tanks will be larger. You need a higher fuel capacity, and finally resulting in heavier new generation vehicle. Luxury also adds weight of the vehicle. Need for lightweighting is the order of the day because we always look for enhanced fuel economy. Other important aspect is environment. Of course, enhanced payload carrying capacity will be another important aspect to be addressed. And you can see a bus in the peak hour, right, which is designed to carry 50, will sometimes try to accommodate 100. Right, that is a situation in our country. If you see the opportunities in lightweighting, of course, one is the lightweight material. So that is the major option. Structural lightweight construction is another option, and the last one is optimizing production process. Under lightweight materials, we always, of course, one option may be high strength steels, but quite expensive. Mostly used in defense and aerospace settings. Aluminum and magnesium is an obvious choice. Then Another welcoming member is unreinforced and reinforced plastics. If you see the optimizing of production processes, of course, we look for light joining techniques and new manufacturing processes. The trends in material use is, as I already said, decreased steel usage, so increased usage of plastics, composite, and lightweight materials. Aluminum and magnesium alloys are becoming the most preferable choice, and yes, reduced toxic materials, which nobody is accepting. Then another important aspect what you need to look here is the increased recyclability. So people normally look for composite materials, and the trends in composite materials are towards improvement in properties of the fiber and this. Enhanced properties of the fiber is always the requirement of the industry, whether it is a automotive industry or aerospace industry or a different segment. The properties of the resin are always improved, right? People develop resins in, of course, for various applications. People look for degradable resin. People also look for resin which can withstand very high temperature, faster and predictable infusion, reduction in number of particles. You don't need to make a lot of parts and assemble it, and cost reduction in various composites. Right, with all the trends, if you look at the composite materials, especially enhanced properties of fiber and resin. And if you see the trend, the key driver is weight shaving. Of course, due to increase in specific strength and stiffness. Of course, performance safety is another major requirement as far as automotive industry is concerned. I don't say it for general application, say a race car, right? You can see on the left, it is a complete monocoque structure made of carbon fiber, and it is actually joined to a metal chassis, right? This is actually a project done by one of my students in Western University, and he shared this. And see, when it looks to safety, and you cannot take it lightly, right? The life of the race car driver is, of course, the life of everybody is important, but it's very, very valuable. You can see the environment in which the race cars are driven, or the speed at which the race cars are driven. You can understand the demanding requirement of a race car. One is performance. Obviously, for a race car, the performance is the key. But more than that, safety plays a major role. CFRP has excellent brake saving potential. Most of the race cars are built by CFRP. Of course, glass fiber composites dominate in aerospace, not aerospace, in the automotive industries too. Uh, Another trend is use of natural fiber composites. We have a lot of scope in that. Issues in composite material, if you see, uh, little has been done to reduce the composite systems cost because it was predominantly with the aerospace industry till now. Scrap rates of manufacturing process are high. You cannot say that all the parts that are produced will be acceptable. The percentage of acceptance is less. And another important aspect is upcycle. Pre-preg layups are really challenging, time consuming, and drilling and assembly of products. So once the product is made and you have to assemble it to either a metal frame or a chassis or a structure, right? Of course, when you go for drilling a composite material, it normally leads into delamination, fiber fraying, spawning, right? That too, when you actually drill along with the aluminum light metal, the chips that are passing through the composite material still spoils the product. So the joining is a major issue as far as composite materials are concerned. We have done a lot of work in this drilling and drilling of metal and composites. The alternate solution as far as use of not replacing composite material, alternate solution to reduce the use of synthetic composite. A synthetic composite is going for green composite. So environmental friendly green composite is one of the alternate solutions we can look into. Natural fibers and thermoplastic composites are the better choice, we believe, because thermoplastic composites you can able to recycle it. Natural fibers, obviously, utilizing the natural resources. So we have many natural fibers starting from straw fibers. You can see corn and wheat, grass fibers like bamboo, etc. Bast fibers, flax and hemp, leaf fibers, these are plura, then seed fibers, fruit fibers. You do have wood fibers from, right? Natural fibers in automobiles are coming up. The options are going for wood polymer composites, especially for the interiors. You can see another example where hemp fiber is made into a woven mat, then it can be made as a finished door and used in automobile. Another major advantage is vibration and noise absorption. Low cost too. One important aspect what I want to tell you here is in our engineering environment, the availability of high performance fibers are really scarce and expensive. We don't get fibers, especially high performance fibers in our country. You can see the various options that are possible in an automobile from the roof interior to bumpers, hood, wheel arch, etc. Even boot base, etc. Right. You can also use it for bus components, composite for bus components. So you have possibility to use it in the roof. You have roof structures. Then you have side structures that are possible. Then you have a complete monocoque structure which you can able to produce it. So which reduces a number of parts assembling into the structure. And you can even use roof handrails or window safety rails. We have actually taken up some work in this direction. We have done composite sandwich. The core material is low strength material, but its higher thickness normally provides higher bending strength and stiffness with overall low density. A lot of the sandwich materials are available in the industry. You can see the application of composite sandwich where both hulls can be made. Flooring panels and roofs for housing applications, of course, paint structures, and it is also used in aircraft panels. And you can see some of the flooring and roofing panels made in India successfully. So we took this as a research topic, and instead of going for a synthetic core and synthetic skin, we tried to use flax is a natural material, and instead of going for a honeycomb structure or foam, we used agglomerated card as a core material. Of course, you can see the flax fibers that are produced in the stems of flax plant. The structure is more crystalline. It is an alternate to e-glass fiber. which you can say that which gives higher or excellent strength. You can see the properties where the E-glass modulus is around 70 to 76, and the flax fibers ranges from 27.6 to 103 G. So this is really a candidate for replacing glass fibers. Since glass fibers are extensively used, we thought, okay, let us find an alternative available in the natural fiber so that it can be used. And we took carcass support. This is another natural material available for us to use, which has low density, high shear strength and modulus, better stiffness properties, good thermal and better acoustic insulation. So more or less we used natural material except a small amount of resin which is used for binding the skin to the core. Of course, we produced this in a vacuum packing technique, and this was cured in a room temperature. We didn't go for oven curing. There is an option we can think about. We can go for oven curing instead of autoclave curing. Autoclave is expensive, but of course, oven can be a cheap solution. We made a lot of specimens, mainly for characterizing the sandwich panels, and we found that the flexural strength is much better than its counterpart. Maybe the material which we try to replace, like plywood or gypsum board or glass reinforced gypsum. So we got better strength. And thermal conductivity tests were also conducted, and we found that the green sandwich has a thermal conductivity of 0.03 to 1 that will help. Another property which we can able to appreciate is this sound absorption coefficient test, where the green sandwich has a coefficient of 0.5. So this is what we have done. Of course, we have done a lot of other tests like impact studies and compression behavior, etc. But more importantly, since we are talking about automobile application, what we need to look at how it actually being disposed, right? Since we use, if you use a lot of parts, then biodegradation is very important. And we could able to find almost very good result, and they passed through that 82% higher than synthetic sand. So this is one of the advantages if you try to use natural fiber and natural material as a whole. Right, of course, this is the conclusion of the array that being composite sandwich made of flax as reinforcement and agglomerated garlic by using vacuum vacuum. The performance were compared with that of the synthetic based composite. We actually made a glass fiber based sandwich at the time, and of course, we were able to get really impressive results. This is very important, right material for the right part. So when you look at a product as a whole, what we need to look at is the performance and its weight. So this is generally attached to the technical aspect. And we have to also look at the market. So volume and price, obviously looking for better profitability and return on investment. So the technical challenges, especially as composite materials are concerned, the manufacturing process. Many manufacturing processes are available. Few are only suitable for mass production. The issue is Q cycles are longer. Another challenge is composite manufacturing process automation. If you look for an automotive industry, then automation becomes a major issue. You need components in mass, and it should be produced in mass. You would have seen in the spray of molding how many people are working, and it requires skill and it requires a lot of labors, and you need to wait for a longer period of time. The third important challenge is the near autoclave performance. The performance of the component should match with the autoclave fueled product. Cost of the materials, yes, carbon fiber manufacturing. Of course, it is not really available in our country. Yes, importing to a larger extent, and the products are cost. If you try to use it for automotive applications, then we obviously look for low cost solutions. Right now, GFRPs are widely used. Natural fiber composite may find really more applications in future. Other technical challenges in the composite manufacturing, especially in the automotive side, is methods of determining damages. So whether the product is really suitable for application. So damage detection and assessment is another crucial aspect. Repair techniques are also limited. So if the part is damaged, then how to repair it? Replacing the entire parts, of course, lead to increased cost, and on the other side, how to dispose it, right? And how to train the traditional mechanic shops. So if there is a small issue in the vehicle, we normally go to a mechanic shop where we handle it without much issue. But when you use composite parts, then it needs to be trained. More importantly, joining techniques, because we are using it in conjunction with the existing metal parts. So it results in multi-material car bodies and will be joined by stable process. One solution may be adhesive bonding, cost-effective and faster. Bonding adhesives are required. So we need to establish procedure for job. The recycling process. Not straightforward as metallic materials. You can just go to, or you can scrap it and somebody can buy and recycle it. But here, most of the time it is assembled by metal fixing. So you have to break it, and disassembly, debonding, and separating are one of the major issues. Cost of recycling is another technical challenge which we need to look into. What you see here is applications of types of composite based on fiber. On your left, you have glass fiber composites, interior, headliner, upper body system, air intake, manifold, instrument panel, bumpers, beam. A lot of parts that are presently made by glass fiber composites. And carbon fiber composites, of course, chassis, a monocoque chassis, a road, tailgate, hood, door panels are made, side panels, rear spoilers, fenders, bumpers are made. But natural fiber composites, mostly the interior door panels, seat pads, load floors are made, and we have a lot of scope for utilizing the natural fibers into the automotive applications. So this is my overview about composites for automotive applications. If you look at a composite for armor applications, uh, I have a small presentation which I would like to share, which is done by Australian Defense Force Academy, where I had an opportunity to visit. High velocity impact behavior of ultra high molecular weight polyethylene fabric reinforced composite laminates. This is actually one of the kind high velocity cruise gun which can able to throw a steel ball at 3,000 meter per second. So this is one of the, this was available in the Aqua Australia. The background is the material that is available in the market, the newly developed ultra high molecular weight polyethylene fibers, and it is sold in the market in the brand name Dyneema and Spectra. So you can see that it is 10 times stronger than steel, but like than more higher toughness and energy absorbing capacity than aramid fibers normally used for launching vehicles. Of course, these Dyneema and Spectra are available in the form of woven fabrics, unidirectional laminated composites, woven fabric reinforced composites. It is normally used for body armor, helmet, of course, small linings. So the objective was to study the impact performance of laminates reinforced with Spectra and Dyneema fibers, and to assess the role of thickness and the fabric architecture compared with different matrices. Of course, ranging from brittle to highly flexible materials. So they took two materials for testing. It is plain beam uh, made of Spectra. Then another one is satin weave fabric made of Dyneema. Four resin systems were used. Epoxy being brittle, so they went to nanoparticle toughened epoxies, less brittle than epoxy, ductile epoxy, then polyurethane. It is proved by polyurethane. So this is the properties of ultra high molecular weight polyethylene fabrics guiding on Spectra, and you can see the tensile strength it is 3.9 GPa, whereas Spectra 2.9 to 3.3. Tensile modulus is 109 to 132, whereas for Spectra it is 97 to 100. If you look at the specific strength and specific modulus, it is much higher than any of the materials that are available for our use. So these were the resin materials, epoxy, then then the ductile epoxy is called as a copol and the poly. Right. So this is about the properties of the resin matrices used, and the methodology is fabricating the laminate by a similar process, which I already told you, vacuum bagging, atmospheric pressure of, and it is cooled using room temperature. Spectra and Dyneema are used, and one dynamo is equal to 2 spectra. So because of the variation in the density. So this is a general schematic diagram of how vacuum bagging is done or vacuum infusion is done. This is the process. And this is the experimental matrix, or what we call it as impact test matrix. So they made board, bulb, and totally 36 combinations, and each sample was tested with three velocities: 113 meter per second, 152 meter per second, and 186 meter per second. Right? This was actually done in a medium velocity impact testing, where a spherical ball of 12 mm diameter was used. The mass of the ball is 7.05, and the gas pressure is available here, and the impact energies from 45, 82, and 133 joules. The target was clamped in a fixture, and a high-speed photography was used. It can able to take 8,000 frames per second. So this is the capacity of the camera that was used to capture the behavior of the composite when the spherical steel projectile hit at a particular velocity. So this is the medium velocity gas gun. You can able to see here, right? This is the specimen, the laminate holder, and this is the clay box. If the ball penetrates through the specimen, then it can be captured by the clay box. So this is the setup. And the damage evaluation was done using visual examination, then backlighting, then three-dimensional deformation mapping. Of course, also captured with high-speed motion photography. So this is about the backlighting. Specimen is placed above the projector and recorded using a camera. Of course, laser scanning is a 3D mapping of residual deformation by laser photography. So this is the results of the spectra samples, where you can see the energy absorbed with the impact, absorbed energy versus impact energy. This is in comparison with dynamo. The other one is spectra, and spectra really perform much better than dynamo. That is one thing. Then about the polymer, we have some results to share, and this is how the impact behavior of steel projectile into the composite. Right? You can see the number of frames per second. So this is the impact. Then try to deform, then the deformation, and finally it breaks out and come. It breaks out and come in a porous fabric panel, and at the bottom you have porous nanolaminate panel, which actually deforms the laminate, and it doesn't actually allow the steel ball to pass through. It actually stops it. Right? This is another one where you have 16S epoxy and the 16S polyurethane laminate panel, and the brittle laminates. Of course, I can say the brittle laminate actually allows the projectile to pass through. It breaks the fibers and allows to pass through. But whereas the ductile laminates, same grade of fabric is used here, and it actually stops the steel ball. But one issue what you have to look at is this. That is what we call it as a bad signature. The amount of deflection or the bending the laminate is subject. Right? This particular material is normally used as a personal protection. We call it a bulletproof vest. But behind this, there will be a metal insert, a light metal insert, so which will not allow the laminate to deform. Right? If it deforms a lot, the bad signature is very high, then it creates damage to the person who is going to use this personal protection device. Right? So this is the comparison of 8D nano and 8D polyurethane subjected to particle impact, and the brittle laminate actually creates a localized fracture. Whereas here is no fracture, but you have a deformation, residual deformations. What you can see here. Right, so this is another result. So the major conclusion was the impact response or ultra-high molecular weight polyurethane laminate is strongly dependent on its properties and thickness. As the thickness and matrix rigidity increases, the impact response gradually changes from membrane stretching mode to plate bending. Among the 4 resins studied, flexible matrices performed better. The laminate panels with flexible resins have higher penetration resistance and energy absorbing capacity. The spectral laminates had higher perforation resistance and energy absorption capacity than the Dyneema counterparts, irrespective of the resin used. I just would like to show you a small video again, where the first impact experiment of this kind was done in Armour, where you can see the high pressure gas gun, or I would say high velocity gas gun available, and they built it for testing bulletproof vest. A lot of papers are available in this particular direction. Hangzhou and Pablo and this sector, along with Paul Hazel, has published more papers on this particular topic, and if anybody is interested, can study. Right. But just to conclude, of course, there is a lot of scope for using polymer matrix composite, especially natural fiber composites, in the automotive industries. And the challenges, as I already said, the manufacturing process, which especially cost effective and time consuming, right? Or low cycle time is very important as far as composite components for automotive is concerned. And other issues like joining techniques are to be studied, then the repair techniques are also to be studied. Cost of the components can come down if you use the material available in your country. On the other side, if you have, if you see for Armour applications, yes, we have these 2 materials that are coming up and more to be developed. So I thank the opportunity given by the organizers for conducting this webinar. Thanks for your patience. Listen. Thank you very much.
Thank you, sir. Thank you for sparing your valuable time. So, shall we take few questions, sir, from the participants?
Yeah, okay. Yeah.
Sure, sir. Thank you, sir. Thank you so much. And sir, and specifically a question I have asked by a participant. For Armour application, how the natural fiber materials can be used? Say, at least give few examples for natural fiber materials which can be used for Armour application.
No. See, as far as it depends, right? For personal protection, you cannot use natural material. Maybe for helmets, again, natural materials cannot be used. But maybe once the exterior is made out of high performance fibers, inside, instead of some foam, we can try for natural materials. Right? The use of natural fiber to armor is limited. My focus is not to promote natural fiber to automotive to armor applications. My focus is mainly use it for applications like passenger cars, trains, bus applications. It cannot be used because the property of those fibers are cannot be matched with the fibers of ultra high molecular weight polyethylene or the requirements of the armor industries.
Thank you, sir. Thank you. Hope you have answered for it. So, next question: is there any specific lightweight material is there as a coating material so that we can enhance the strength for automobile application?
Lightweight material as a
yeah.
coating.
Yes, sir. Same. I hope he wants to ask automobile application any natural fiber material with some coatings. I hope so, sir.
Coating material, of course, treatments are done as far as fibers are concerned because to enhance the interface between the fiber and the matrix. That is possible, but no specific coating material is available. I have not come across, but generally treatments are done.
Okay.
Fiber treatments are done.
Okay, sir. Hope you have answered for it. And, sir, one more question is all about: can we use magnesium alloy for automobiles for
Of course,
lightweight application?
yes, it is coming up. It is coming. People are looking for since the process, the technology, the processing technology needs to mature in our country, but surely this magnesium alloy will take up.
Fine, sir. Thank you so much. And please discuss about the machining of sandwich composite materials.
Yeah, it is a big challenge. Of course, we have done a lot of work, as I already said. Sandwich in the sense, we actually work with, we call it as a multi-material. So we have polymer matrix composite as one layer. Then sometimes titanium alloy or aluminum alloy is another layer. Especially aircrafts are built using titanium and aluminum panels along with polymer matrix composite, predominantly carbon fiber. So when you go for drilling and assembly, it is a big issue. A lot of work is done, and the challenge is the temperature. So when you drill carbon fiber, you have issues like fiber pull-out, delamination, etc. When the drill pass through metals, then the hard chips that are going to come out of the hole will create damage to the composite. So that is very big issue. Especially if you drill titanium, then you find it a big challenge. And especially if you look at the aircraft structures, millions of holes are drilled, right? So when you go for such a huge number of holes, the life of the drill is involved. And when you go for again huge aircraft structures, you take the machine to the product, and supplying coolant is not a solution. So it has to be done under dry. The drilling has to be done under dry conditions. So to overcome this evil, of course, a lot of research is going on. We do have some publications in this one. But if you look at sandwich with the skin and the core, yes, it is another issue. Right? You have to characterize. Not much publications are available in this particular purpose. We have not tried drilling of sandwich, but there is a scope to study this particular process. Of course, it is not with respect to damage. It should be done with respect to the mechanical strength of the product. If you drill a hole and join with a steel or a structure, any other structure, then how the joining strength. So the joint strength is important, or what we call it as not the whole strength is important.
Fine, sir. Thank you, sir. So next question is all about what is the temperature range of the composite which natural fibers can hold? I think he wants the temperature range wherein the natural fibers can withstand. I hope so.
No, it is not directly a natural fiber.
Okay.
We don't use it directly. See, it is actually composite is a combination of two material at least, right? You have the resin and the fiber system, right? So if you use polyester, then the temperature may be less than 150 degrees centigrade. If you use epoxy, it may be it can go up to 180 degrees centigrade. But when it is exposed, the fiber is exposed or more seen on the surface, then it obviously degrades. Right, so of course, it cannot be directly placed where it is subjected to very high amount of heat. You have to select judiciously. Right, you cannot use a natural fiber to a component where it is going to be placed very near to the engine. Yes, that's a good question. One has to judiciously select based on the fiber and the matrix system.
Fine, sir. Thank you, sir. And one more question is all about which type of advanced composite can withstand transverse loading condition?
Transverse loading.
Yes, sir.
It means, see, the composites are designed. I would say it is based on the layer sequence, right? There is something called longitudinal and transverse. So if a product is going to be subjected to tensile, maybe unidirectional composites are better. But if the composite is subjected to multi-directional load, then you have to decide the layup sequence. So you have to go for maybe a quasi-isotropic layup sequence. So different types of layup sequences are available. So you probably would have heard about unidirectional, bidirectional, woven fabric. Woven fabric can be an example for bidirectional, but when you are using unidirectional prepress, then you have to look at how the layup sequence of the laminate is going to be made. So when you properly design the layup sequence, of course, a product can be subjected to either longitudinal or transverse loading.
Thank you, sir. Please give some advice for the people, those who are doing research in nano composites.
I'm not an expert in composite, but there are avenues. See, the issue is most of the time, especially with the composites, we end up with simply characterization, right? So if you do simply characterization with various combinations, getting a favorable result or getting a very good publication is difficult. We have to look at for what application we are going to do. So if you talk about nanocomposites, then again we look at for what application you are aiming at. Then the processing, right? We should look at how the processing is going to be. A proper way of preparing the laminate is very important. Otherwise, you don't get interesting or impressive results.
And one question, sir. What are the NDT methods available for composites?
Yeah, there are many. You have ultrasonic, then you have infrared techniques. There are many techniques available. Even then you can go in depth in the three-dimensional. You can find out the flaws in the system. I don't immediately remember the techniques, but NDT is not used. A lot of non-destructive evaluation techniques are available for composites.
One related question. So, what are the uses of polytetraethylene in automotive?
I'm sorry.
That's what I found. Actually, it just directly couldn't answer.
Polytetraethylene is a resin, right? It's a resin system.
I hope so, sir. PTE.
Yeah, polytetraethylene.
Yes, sir. And is there any specific surface finish technique available for natural fiber composites? Surface technique.
What people used to do is they don't worry about finish as far as the composite is concerned. The texture is important. If you really want a good finish, then you go for using vacuum bagging. Then in the vacuum bag preparation, we have some specific materials. So we call it as a pre-ply. We have a breather. Then we have again a glass fabric which is placed over the laminate, so which gives a natural finish. A better finish can be achieved. And the bottom surface of the die is normally transferred to the bottom surface of the laminate. So there will be no specific process to improve the finish like a metal part. We normally produce the component to near net shape, right? So if you are, for example, if you look at a helmet, right? Helmet really need not have a very good surface finish. But if you want a finish, then you can apply some gel coats and you can go for some painting, etc. But for its general applications, we don't normally look at how to finish it. The resin itself will give you the natural finish, that's all.
Fine, sir. Thank you, sir. So one last question. Importance of TGA and DTA methods for testing in this advanced composite materials.
It is a specific process. A lot of work is done on this. I have not done on TGA. So much characterization I have not done. I was mostly involved in processing and manufacturing of the composite parts. not gone into the PGA.
Fine, sir. Thank you, sir. I hope there is no question. Thank you so much, sir, for your valuable insights. And specifically, we have got good response in the chat as well. And we are, as a KPR Institute of Engineering and Technology, on behalf of the management and head of the department of Mechanical Engineering Department, we would like to extend your warm support, and we really thankful for the insights provided by you, sir. And very specifically, people have mentioned about mostly people have seen automobile applications of composite materials. First time we have introduced how the armor applications can be have some implication of this particular natural fiber materials also. And thankful for showing the your experience about our testing of the armors using our gun. And thank you so much for your insights provided by you, sir.
Thank you very much.
Thank you, Dr. Krishnaraj, for having made a very sharp, very specific, and very nice presentation. Thank you so much for your presentation.
Thank you, sir. Thank you.